Okay, so we are going to start the tutorial 4, where we'll be continuing with the instructions or the language of the computer. And here we are actually talking about ARM instructions. And this is the content that we'll be covering today in the tutorial 4. First, we'll be looking at character data, how you can handle character data in assembly, which actually will be very similar to the way you handle other integer data, but there are small differences. And then we'll talk about byte half word operations. Actually, here we will be talking how you can handle character data. First, we'll look at what character data is, and then we'll talk about how you can handle character data. And then we'll be looking at a string copy example, where you will be looking at how you can copy one string from one place in the memory to another place. And then scanf and printf examples. So you will be learning how you can use these library functions, scanf and printf, to get something from the user or print something to the user. So this we'll be looking at. Actually, they were there in your skeleton codes. Printf was used in your skeleton codes, but we did not discuss about that formally. But here we'll look at that, and then linking and loading. We'll talk a little about how a program is linked and loaded. So this is not something to do with strings and characters. That is about how a program is linked and loaded so that it can run or get executed. So this also we'll look at in brief. And first we'll have to see what this character data is. So there are 2 byte encoded character sets, which is used to handle character data, that is things like strings. So inside strings you need to have characters A, B, C, D, things like that. So these things at the end of the day have to be converted into something the computer can understand. So that something is binary. And so for that we have to use a certain number of bits and also encoding standards. So there are 2 encoding standards, primitive encoding standards. The first one is ASCII. So this one, I think most of you have heard about this ASCII and ASCII table and things like that. So with ASCII encoding standard, you can represent 128 characters. So the way these characters are encoded and what is the number that is used to encode an A, encode an B, so things like that are there in the ASCII standard, and you can refer to the ASCII table to get those details. So with ASCII, we can represent 95 graphic symbols, and there are 33 control symbols, or control symbols. So these control symbols actually were used to things like new line character, things like that, tab character. These things also are encoded in ASCII, can be encoded in ASCII. So these things we call them control. And there's another encoding standard which is called Latin 1, and it supports 256 characters. So it can encode 256 characters. So what it supports are basically it supports all the characters supported by ASCII and also 96 more graphic characters. So that is what these 2 standards are. And then we come to this modern encoding standard, which is called Unicode. I hope you all have heard this term, Unicode. And with Unicode, you can have a 32-bit character set. Now, earlier ones, to represent 1 to 128 characters, how many bits do you need to have? 128 different combinations you can achieve with how many number of bits?
Seven bits.
Yes. So with 7 bits, you can achieve 128 different combinations, and therefore different characters. And for Latin one, since it supports 256 characters, it needs to have 8 bits to represent all these characters. And so with that, with 8 and 7 bits, you can only go for 128 and 256 characters. But in Unicode, we have 32 bits. So I think you can do the calculation and find the number of different characters Unicode can represent, right? It is going to be a very large number, because these bit numbers, they are going to be exponential. So when you increase 1 bit, it's the added number of characters are going to increase in an exponential way. So 32 bits. With 32 bits, you can represent a large character set. And this one is used in Java, C++, wide characters, and most of the world's alphabets plus symbols. So most of the world's alphabets can be represented or can be encoded with this Unicode standard. Because you have 2 to the power 32 characters available in the character set. And UTF-8, UTF-16 variable length encodings are there. So different versions of Unicode. Right. So that's about the basic details of character data. And then we come to these byte or half word operations, where we actually handled these character data in ARM assembly. Right. So now ARM supports byte load store. I think we discussed about this in brief somewhere earlier, where we talked about memory operations. So with just LDR and STR instructions, when you perform memory operations with LDR and STR, you are loading or storing a word from memory or to memory. But when it comes to strings, you don't need to actually load a full word or store a full word in the memory, because a byte or a character can be represented with just 1 byte, right? So when you want to load a character from memory into one of the registers in the register file, you can use these special instructions, LDRB and STRB. So these instructions have been made available in the ARM instruction set because they are common. So these byte load and storing is common, and if in order for that to be faster, since it's common and we want it to be faster, like when you load a word from the memory, it's going to be slow compared to loading a byte. So we have these special instructions, LDRB and STRB. So with LDRB, you can load a byte from memory into a register, read byte from source. And this syntax is very similar to the way you work with LDR, just LDR instructions. You have the destination register first, and then the memory location, base address, and the offset. And then STRB, it's used to store write byte to destination. That is storing a byte in the memory. So that syntax is also very similar to, and it is the same as it is with STR instruction. And then there's this sign extend to 32 bits. So this maybe is not common when you handle with when you deal with strings, because for strings, the sign extension is not really needed, very much needed. But when you are loading a byte from the memory, you can extend the sign. So this also we discussed a bit, like in brief, when we were talking about memory operations. So LDRSB, this instruction, you can use it to load a byte from memory into one of the registers and then extend the sign. Sign is the most significant bit in the byte which is loaded from memory, and that most significant bit, we'll be replicating it 24 times to fill the leftmost 24 bits, because a register is going to be 32 bits now. So if you load a byte from memory, you are going to left with 24 more bits, because a byte is 8 bits. You have 24 bits more. If you just execute LDRB, the leftmost 24 bits will be filled with zeros, all zeros. And if you execute LDRSB, these 24 bits are going to be filled with the most significant bit in the byte you are loading. Right? That is actually what we are calling the sign extension. Was it clear, this idea about sign extension and byte load store? Clear? Okay. So I'm getting a response only from one person, and I'm assuming the response for others also is the same. Like, if you don't understand it, you can ask me to explain it again. Right? So so then we come to this ARM half word load store. So we are done with byte load store, and half word load store for like half word is 16 bits, byte is 8 bits, and half word is a half of a word, that is 16 bits. So for that you can use these special, like there are another two special instructions which are there for half word operations, LDRH and STRH. So LDRH, you can use it to load a half word from memory into another registers. And the syntax is again similar to LDR and LDRB. So you can read half word 16 bits from source and load it to a register. And STRH, that is to write a half word to the destination location in the memory. And similarly, as it was with the byte sign extension, you have sign extension for half word loading as well. So LDRSH, you can use this LDRSH to load the half word from the memory and extend the sign to fill the leftmost 16 bits. So you are going to be left with only 16 bits, because 16 bits are going to be filled with the original value, and the remaining 16 bits you can fill it with the sign if you do this LDRSH instruction, or perform this, execute this LDRSH instruction. Clear? It's also very similar to byte load store. Okay, good. So here we come to this string copy example that I was talking about in the content page. And this example, you can see the C code that we are trying to compile into ARM assembly. This actually is a function. We have implemented it as a function, strcopy, strcpy. We have a null terminated string stored in the memory. We have a null terminated string loaded to memory, which is stored in the memory, and we want like that is actually an array. So you all know in C, a string is a character array. That I think you know. That idea you have, right? a string in C, or any like at the lowest level, it's going to be a set of bytes anyway. So in C, when you are dealing with strings, that's actually an array of character data that is very close to what happens in the hardware. So in other programming languages, you have things like strings natively supported by those languages, but they are not going to uh, be stored as like simple. So they are not simple primitive variable types. So char, int, those are the primitive types, and a string, something like a string also, you have to something like a string is actually represented or stored as an array of characters, char variables. So that idea you have, right? A string is, do you have it? A string, an idea that a string is an array of char. Yes, you have, because you have done this programming course. So so we have a string stored in this y char array, and we want to copy it to x char array, right? And that in C you can do easily with this code given in the slide. We have a I variable which is used as a counter, and then we make I equal to 0. Actually, we are not going to do I. We are using I to index the char array. And if you have any issue in hearing me clearly, let me know. If there's any, yeah, lag is okay, but if the voice is getting broken or something like that happens, let me know. So we have this while loop, and I is used to index the character element in the array, and then what we are doing is we are making xi equal to yi as long as we have not come to the null terminated null character, right? A character, a string is terminated by appending a null character at the end of the char array, no? So that also I think you know. So this null character is this one \0. So we are checking whether the I is equal to this null character. If not, we are going ahead with this while loop, making xi equal to yi, right? So that is what we are doing here. And addresses of x, y are in registers R0 and R1 respectively. So base addresses of x and y, and I is in register R4. So we are going to look at the assembly code. So this is the ARM code, the compiled ARM code for the previous C code. And since this is going to be implemented as a function, we have this strcpy label, and then we are going to use the R4 register, right? Can you remember the conventions we had? If we are going to use R4 to R11 registers, we have to preserve them in the stack. If you are going to use them inside the function, our convention is to store them so that the main program knows that they are not going to be changed. So R4, if you are going to use R4 inside a function, you need to preserve that in the stack. So that is the first thing that we are doing. R4 actually is used for the I index to store the index. So we have sub SPSP #4, that is to adjust stack for one item, and we then store the value of R4, that is the content in R4, to the stack SP #0, and then we load R4 with 0. That is, we are making I equal to 0. And then we come to the loop, the while loop we had in the C code. So inside that loop, what we are doing is, for that we have this L1 label, and now you need to calculate the address of yi, right? We have the base address of y stored in register R1, and also we have the index I, the value of index I, and with that we actually can calculate the yi, ith element in y. To do that, we can just perform this add operation, add R2, R4, R1. So the address or the location that we need to access is going to be computed into in R2. So that is going to be stored in R2 after you perform this add operation in the L1 label. So R2 now is going to contain the address of yi, and now you can perform this LDRB operation, since we need to only load a byte from memory, right? So if you have tried loading a word from memory using LDR, so these memory locations, so this is like a added additional thing which might be important to some of you who are looking for more details. So LDR, when you use LDR, you have to, these offsets have to be aligned in the memory. So 4 byte locations only you can access. So this offset, if you put something like #1, #2, then if that memory location is not something byte aligned, word aligned location, it's going to behave in a way that we don't know. So sometimes it can give an error. Otherwise, it might behave in an unexpected way. That is valid for LDR operations, where we try to load the full word from memory into a register. But with LDRB, that word alignment thing does not apply here, because we are loading bytes from memory. We are telling the processor to load just bytes. So with LDRB, that alignment thing is not there. And that is, these actually you can say when you perform this, they are byte aligned in one. So #0 in the memory, actually they are going to be word aligned, but you can access each byte separately inside that word by having offsets like 1, 2, 3. So R2 #0 we are using because we have already calculated the memory location to be accessed. So that actually not necessarily be a multiple of 4. So these are all additional stuff. If you don't understand them, you can let me know. And to continue with the rest, actually, just having the basic idea is also enough. But if you need more details, you can think about that as well. These things are actually important. So LDRB, using LDRB, we are going to load a byte from memory into R3 register here. That is, we are going to grab ith element of y and store it in R3. So #0 we are putting it here because we already have calculated the proper address with this add operation we did earlier. And then we calculate the address of xi and store it in R12 by performing this add operation. Add R12, R4, R0, because R0 is having the base address of x, and I again is in R4. When you do this addition, you get the location, memory location of xi. And then now we have loaded the yi value into R3, and now we want to store it back in the meaning we want to store it back in the memory, but in a different location. That is because we are copying yi into xi. So for that, again we are using strb, store byte operation, and r3, there needs to be a comma here. So r3 comma r12 hash 0. With this, we are actually performing our intended operation xi equals yi. And then we are comparing R3 with 0. R3 actually now contains what? At this stage, R3 contains what? R3 contains what? Now I am here, compare R3 hash 0. R3 contains what? Yes, yi. So R3 contains yi. We are actually checking whether yi is the null character to terminate the while loop, and also to finish this copy thing. So we are checking whether yi is 0. So the null character is represented with 0. That value, so null character is stored in memory in a register in computer at lower level, at hardware level, it's stored as 0. So the hexadecimal or binary or decimal representation of null character or encoded value of null character is 0. So that is why we are checking R3 whether R3 is 0. So we do that comparison, and then if it is equal to 0, we branch to L2, where we try to finish the copy thing, or str copy, where we are trying to return from strcpy function. So if R3 is equal to 0, we branch to L2. If not, we go to this add R4 hash 1 instruction, where we increment I by 1. So I equals I plus 1 thing we are doing there, and we do an unconditional branch to L1 to go ahead with the next iteration of the loop. So BL1 we do it, and then I hope you get the idea. Then when we come to L2, what we are doing is we release the stack space we allocated for storing R4, for preserving R4. So you restore the value, the register R4 with this LDR R4 SP hash 0 instruction, and then release the stack space by adding stack pointer, incrementing stack pointer by 4. And then finally we return from the function by executing this instruction, move PC LR. Was it clear to you all, this example? I hope it's clear. What's in the reg R1? R1 actually contains the base address of Y. Here you can see base address, addresses meaning base address. If you say an address of an array, that's going to be the base address of this array. So base address of Y is stored in R1. Correct? Yeah, good. Others? Any more questions? Is it clear? Can we go ahead? Is it compulsory to use R12 for that add instruction? For that add instruction, actually, we have used R12 because if you look at the convention, you don't need to preserve R12 when you are using it inside a function. So it's easy. If you use another register, something like R4 to R11, like R5 to R11, then you need to preserve it in the stack. So R12 is not expected to be preserved by the callee. So you can go back and look at the convention we had, ARM register convention. You can look at it and have a look at that, and realize that R12 is not needed to be preserved by the calling. So that is why we are using it actually here. So you can use something like R5, but if you are using it, you need to preserve it in the stack or store it in the stack first. The original value of R5, you need to save it in the stack first, and then when you are returning from this function, you need to load it back to R5. Got it? Okay, I'm getting a private question. Can you explain strb and ldrb part again? Here in this example, strb and ldrb with related to this example, I guess you're asking. Asus. Asus. Yeah, okay. So strb, ldrb, we are using it to load the byte from memory, and the location in the memory that stores the byte we need has been calculated by this add instruction. Now, say for example, R1, the base address of Y is something like 0. Yeah, we will let it be 0, right? So the address of yi, the base address of y is 0, and I now is again 0. So you perform this add operation, and 0 plus 0, that's going to be 0. So R2 is going to contain 0. And with LDRB, you go to that 0th location in the memory and you grab only 1 byte. With just LDR, we are not only taking 1 byte, we are taking a full word. That is 0, 1, 2, 3 locations are going to be fetched from memory, and they are going to be loaded into a register. But here with LDRB, load register byte, with this instruction, we are going to take only 1 byte located at that specific location. Right? So at the 0th location, the byte at the 0th location, we take it and put it into R3 register. So at the next iteration, I will become 1, and y, again, the base address of y, I told it, we are assuming that it is 0. Base address of y is 0. And at the next iteration, I is going to be incremented by 1 if we have not come across with this null terminating character yet. We are going to go ahead and come to the second iteration where we have I equal to 1. So R1 now is again 0 because y, the base address of y does not change. So it's the same. So R1 is 0 and I is 1. So you do this addition and you calculate R2, or the so once you are done with that operation, the R2 is going to contain 0 plus 1, that is 1. So now the byte in memory that we need, the location in memory that we need to access is 1, right? So now the first location in the memory you need to access, so that you can do by using this LDRB instruction. When you perform LDRB, R3, R2, #0, you don't have an offset here. That is because we have already calculated the location we need to access. We don't need to have an offset for that. So that is why we are having 0. So these things actually, we have seen these things earlier as well, calculating the memory address first and having offset then. So now R2 is 1. So location 1 in the memory is going to contain another byte, and that only that byte we are going to load from memory, not a full word. When you use LDRB, you are not going to load a full word. Actually, when you want to load a full word, you can't access things like 1, 2, 3. You can only access multiples of 4. That is because this memory is word aligned. So when you are performing LDR instruction, not LDRB. When you are performing LDR instruction, the locations in the memory that you can access are going to be multiples of 4. So things like 0, 4, 8 you can access, but not 1, 2, 3, 5, 6, 7. But with LDRB you can do that because you are only accessing a byte from the memory. Accessing meaning you are getting only one byte loaded into a location. Was it clear? And then store again is very similar. Yeah, seems like he understood it. So in here, two characters are compared, right? Two characters are compared, meaning in the while loop. This actually is not a comparison here we are doing. This is like a compact syntax again that you can use this syntax maybe is not maybe you have not seen this before, but it's again like a compact syntax that is used to do an assignment to another variable, and also we do a comparison. The real comparison is done with this null terminating character with this not equal to operation, comparison operation. But here it's not a comparison actually. This is here what we are doing is we take yi and make xi equal to that one. So this is like a compact way of doing the while loop to perform the operation we need. Or else you can have something like while yi is not equal to this null terminating character, inside the body you can have xi is equal to yi. So this is a compact way of doing the same thing. Got it? Here we are not comparing to characters. Here actually we do a comparison. This comparison is to check this comparison is this one. The CMP we have in the ARM assembly code is for this comparison where we check whether yi is equal to null terminating character. We check whether yi is not equal to this one, and if it is not equal, we go for the next iteration and so on. If it is equal, then we exit from the loop and exit from the loop and return the function. Got it? Shamika. Do I need to like write the expanded or the expanded version of this code if this compact version is not clear? Shamika, are you still not clear? If you are not clear, it's going to be something like this. If you write it in the usual way. Okay, you are clear. Yeah, if you are clear, then we don't need to write it. If somebody is there who is not yet clear with what we are doing here. Xi equals yi and I plus plus. So this is like an expanded version of this same code. So this code will do the same job. This part actually I expanded it. So this is what we are trying to do. We are checking whether yi is not equal to null terminating string character and perform this one, right? And then Sashini is asking, can we use R1 hash R4 instead of R2 hash 0? No, actually, this hash thing you need to use it when you are using immediate values, and whether the offset can be given in a register, that you need to check. Actually, that is not typically supported by ARM, so that is why we calculate the offset or the correct location in the memory that we need to access first, and then using this R2 hash 0, we access that location. So the offset, it has to be given as an immediate value. So it can't be a register value. So that is why we do all these things. Otherwise, we could have done it with the way you suggested. So hash R4 is anyway, there's not, so hash is actually we are using to represent immediate values. So just after the hash, you will see only immediate values that is just numbers, things like 0, 1, 2, 3. So you are not going to see register names after hash. That is because immediate values are represented with hash, right? Hope we can go ahead. Any more questions? It's good that you asked question. That means that you were focusing and trying to understand. So is it all? Can we go ahead? Clear? So the next important thing is this. And once we are done with this, actually, you can do the lab exercise, and we'll look a bit and brief. We'll look at this loading and linking thing as well. But these things you need to be crystal clear with all what we are doing here. Can we move forward? Everyone? Any questions with the related to the string copy example? Are you all sleeping? We have 38 people, members here, students here. If you are clear, then you can say clear so that I can see the number of. Okay. Okay. Yeah. Okay. So seems like it's clear to most of you and all of you, I guess, because if it was not clear, you can say not clear. And then we look at this scanf and printf functions. So how you can call scanf and printf functions using assembly. And we all know that we use scanf to read the number from std in standard input, and we use printf to print something to the standard out or std out. So these two functions you have come across in your C course, and we are going to look at how we are going to use these functions. Actually, it's very similar to the way you call a function in ARM assembly. That is because these things are again functions, just functions, right? So they are also functions, but they are not defined by us. They have been defined by some other people, and these are library functions. We can use the library functions, or we can call the library functions the same way we call another function in ARM. So here now, if you can remember, for scanf, the arguments that you are giving are now you can. So if you look at this code line here, so the scanf call in C would be something similar to this one. Scanf, you first give this formatting string. You specify the what is the format of the input that you are reading. So you use this %d if you are going to read it as a integer, If it is a character, you have this percentage C and things like that, you already know. So that is the formatting string. That is the first argument actually. That is the first argument to this scanf function. So the scanf is a usual function, library function that is defined by somebody else, but it's again a function. And there are two arguments given to it. The first one is the formatting string. And the second one is the location in the memory that you want to store that specific value that you are reading. Can you remember that thing? Because for the scanf function, the second argument is actually an address, if you remember. So the second argument is not like a variable, but the address of a variable. And can you remember that? In C, when you, so that idea you need to have here. Otherwise, yeah, you can remember, right? You should remember. So the second argument is a address. Is an address. So that is because we are going to store the read value, the value we are reading, into that location in the memory. So so that location in the memory, for that location in the memory, when you deal with this scanf in assembly level, you actually need to tell need to specify the location in memory at a lower level. So the location in memory that we access is the stack, right? So unless we are using this malloc and all that, it's going to be the stack that we are using in functions. So here the location in memory that we use to store the value we read from the user is the stack, and that location we can specify with this stack pointer. And now if we want to store something in the stack, the first thing that we need to do is to allocate some space in the stack. So that we actually do by decrementing the stack pointer sub SPSP hash 4. When you perform this operation, you decrement or decrease the stack pointer by 4. That is because we want to read a uh, full integer. In this example, we are trying to read an integer. So we are going to get the need of storing an integer in the memory. So we reduce the stack pointer by 4, and that is so stack pointer now is pointing the location that we have allocated in the memory. So the allocated, and now the next thing is to load. Now we want to call the scanf function. So before calling a function, what do we need to do? Before calling a function in C, or in like more precisely in assembly, before calling a function, we need to pass arguments, right? These passing arguments again has to be done using just the registers we have in the register file. So in the conventions, if you can remember, we are using R0 to R3 to pass arguments to functions. So the two arguments that we are passing to the scanf function are the first one is the formatting string, and the next one is the address of the location in the memory that we need to store the value being read. So we have allocated memory to store the value we are getting from the user, and also so that we have done. And next we need to load R0 with the address of the formatting string. Actually, the formatting string again is a formatting string is again a string, right? It's a string, but it's a constant string, right? So it's not something we are getting from the user. It's a constant string. So for that we use this dot data portion of the program. So if you can look at here, so can you, I think you all can see my cursor. So this location dot data section, actually we use it for storing static data. So static data, if you can remember, so we like inside a program you have this text segment and then data segment, yeah, things like that you have in the program. So dot text segment, that segment we use it to store the instructions of the program, and then dot data section we use it to specify the static data used in the program. So these formatting strings actually are typically stored in the data memory, or the static data portion of your assembly. So this format S is format S is again a label that we are giving to this formatting string. So format S, we specify this label for that, and then ASCII Z, that this directive, this is like a assembler directive. So this directive we are using it to tell the assembler that everything that we are specifying after this one, that is I'm specifying that in ASCII. So if it is just like something like this usual string, so something like that, this we are specifying here, but it's you need to know we are directing the assembler that everything that we are storing, that we are specifying after this one, has to be read as ASCII values. So since these strings are easy to be specified in ASCII rather than looking at the values corresponding to ASCII values, the ASCII values correspond to these characters and putting them here. You can use this ASCII assembler directive to direct the assembler to recognize them as strings, ASCII values, right? So format S, we have a label, and then this one formatting string we have, and with this LDR are not equal format S, this syntax, actually this is like a pseudo operation in assembly. So where this might be converted into, like this will be converted into a real ARM assembly instruction or a set of instruction that will load the address of format is string into R node. So this is a pseudo operation. If you want to look into more details of pseudo operations, you can actually use Google as well and search for pseudo operations. So there are pseudo operations in ARM assembly which can be used to again, that is like a telling, like directing assembler. So assembler will convert into real instructions that will so this is like to make the programmer's job easier. So you don't need to calculate the address of format is uh, the place in the memory that this format test string is going to be stored, and put it here and load R node with that address. You don't need to do that yourself when you use a pseudo operation like this. So after doing this, actually what happens is assembler checks the memory location that corresponds to this string in memory, the location in the memory that stores the string, and loads that memory location, the address of the memory, into this R node register. So R node, the first argument to the scanf function is the string that we are going to format string that we are going to use. So that you can do by using this pseudo operation, right? I hope it was clear. So the way you use the scanf and printf, it's going to be very similar to what you see here. So you don't need to like do rough modifications to this when you use scanf and printf. So, and we are done with the first argument, and then the next argument is to tell the function scanf function where we need to store the value being read. So that actually the values we are going to store in the stack, and then stack pointer. If we use the stack pointer, you can specify that location in the memory, right? So for that we use this just move instruction because we already have calculated the address in the memory. So that actually calculation meaning SP register is now containing the current stack pointer. So we specify that address, or we pass that address to the function scanf by loading R1 with the value in stack pointer. So the second argument now is going to contain the address of the memory location where we need to store the value being read by the scanf function. And then finally, once we are done with the argument passing, we can go to the real instruction where we branch to the scanf function, branch and link to be more precise, and to be accurate, you need to use BL, branch and link scanf. So this thing you are very familiar with this function calling. We already have looked at it. So BL scanf. Once you do that, you branch to the branch and link to scanf function and perform the operation, and then it will return. So that scanf implementation, we are not doing it ourselves. That is implemented by the people who wrote these library functions. So that's it. And then now we need to display or output this number we read to the user, right? For that, what is the function that we can use? When you want to give something to the output, what is the function that we want to use? This is like a very more simple question. Yeah, printf, that's good. I want to get a response from you to see whether you are focusing. So printf, using printf, we can print the value being read or any other variable value we want to print out, so that we can do with the printf function, right? So that is exactly what we are going to do next. Instead of printing just another variable value to the user, we are going to print out the value that we read just a while ago using the scanf function, right? So now the value we read is now stored in stack, and we want to, and now for printf, the arguments to printf are what? For printf, so the C syntax is not given here. For the printf, the first argument is the formatting string, right? And then after that, you need to pass the values that should be put into the placeholders that you have in the formatting string, right? Can you remember that? Yeah. So the first argument is the formatting string, and the arguments after that are the values that you need to print out, or that is actually the values that should be replaced, like that should be put to the placeholders that you have in the formatting string. So for example, now we are going to use this formatting string here, format P, this one we are going to use. The number is this one. So that for that we have a placeholder %t. So this has to be replaced by the real value. Now the real value we need to replace this with is the value we read just a while ago using scanf. Now that value is now in stack. Something in stack you can't just easily pass to printf. You need to first load that value into a register that we use to pass arguments to printf. So the first argument is our formatting string, which is going to be, which should be passed with R node, and the rest of the arguments you need to pass using the next registers R1, R2, R3. So now R1 has to be loaded with the value we want to print, that is now in the stack. So we need to load it to R1 register. So that is what we are doing here. SP has 0. Now we are done with like the value we loaded or stored in the stack. Now we have loaded into one of the registers. Now we don't need that stack space anymore. So we can release that stack space by adding the stack pointer or incrementing the stack pointer by 4. So that is what we are doing here. As soon as we are done with something that we stored in the stack, we need to release that stack space. So that is also one important thing that has been practiced here. If you look at it here carefully. So once we are done with this, stack is released, because in the printf also it's going to use the stack for some other things. So we need to release the stack space that we gained for something in the code, and if we don't need it anymore, we need to release it as soon as possible. So SP hash for that is there to release the stack space, and then we load the format p string into R node. That is actually the base address of that string array, or the character array, or the string. We load it to R node using the pseudo operation again, and then we branch and link to this printf function, printf label. Right, got it? Now another important thing is mentioned here. ASCII are for string literals, and assembler inserts this null terminating character after the string. So that is done by the assembler automatically. So that also is one thing that you need to know. Yeah. So seems like some of you, and yeah, 3 of you have understood. Others, what happens if I change the third line of code? Third line of code as move R to SP. Yeah, that you cannot do, because the scanf function, the way you give arguments to the scanf function are, you specify the first argument in the like it has to be in the same order that you give the scanf the arguments to the scanf function in C. So inside the scanf function, it's again a function, so it reads the values starting from R0, the values passed on to it as arguments. It starts reading from R0, and the address, it expects it to be in R1. So it does not expect it to be in R2, right? So yeah, so that is how it works, because scanf is something implemented by somebody else, and we want to use the conventions. So so that is the case here. Like with the assembly, you have to follow these conventions, because the assembly actually can't know these things. So it will not be able to give you errors about these things, because all what we are doing is you are putting values into registers and branching and linking, and those basic stuff we are doing. So the knowledge the assembler has is very minimal, so it cannot give you errors. So that is why when you are programming with assembly, you have to be really careful with what you are doing, and you have to know what you are doing. Yes, null terminating string actually is encoded with value 0. So for example, now for character A, you have something like, I can't remember actually, something like 65. For character, yeah, like character A is encoded with 65. That is 65 represented in binary with 8 bits or 7 bits if it is ASCII. So that representation is there. Similarly, so for null terminating character, the character is encoded with 0. So you have to know what's inside the predefined functions before using. That is there, but if you go ahead with the usual convention, you can actually, now if you have, yeah, the way you need to pass arguments and all that, actually the order in the order of the arguments that you are passing to the function, this you need to know. Actually, you need to have that knowledge. Even when you are doing it with C, you need to have that knowledge. No, you can't pass the formatting string second and pass the address first. That you cannot do. No, when you are using scanf, there's a standard way of doing it. So unless you don't follow it, you can't get the expected behavior. When you are using it in C as well, I'm talking about it. So when you are using scanf in C as well, you need to have some idea about the way the function has been implemented. Has been implemented meaning the way it accepts arguments. That is all. So you don't need to know the internal implementation of the function, how it is printing something to the output, to how it takes something from the user. The fine details, actually you don't need to know, and you can't know if it is not open source. So usage you need to know exactly. So the order of arguments passed on to it. Right. You have like online material are there to know what those, the way you need to use the scanf and all that is there. Like there are documentations. You have used it so many times in C that you think that is that is part of the usual syntax. That is what. So if you are going to use something that is not common, actually first thing you need to do is to go and check the documentation to see how it works, to see how the arguments are passed. So now here, if you look at the tutorial 4 files, you can see there are example skeleton codes given to you. These things you can use: read two integers x and y, and then print the x plus y value to the output, standard output using printf, and then read two integers x and y, then print the x into 2 to the power y. This also you can see how you can optimize that, since you are multiplying x with 2 to the power value. And then write an ARM assembly program to read two numbers and print whether they are equal or not. So those things you can do. Only this scanf and printf parts are new. And example 5, write an ARM assembly program to read a number n and print numbers from 1 to n. And 6, write a function to find string length and call it from main. So a string copy function, we looked at it, and this one is maybe a bit easier compared to that. You need to find the length of the string. For that, you will have to look at the null terminating string to see whether you have come to the end of the string. Any questions so far? So we are basically done with these assembly instruction stuff. So yeah, whole course as well we are done. So there are specific stuff details. If you want to look at them, you have the basic idea. Now you can go ahead and look at the instruction set, and there are good documentations where it give details about all the instructions available in ARM, especially these pseudo operations. Now these things actually are going to be converted into basic operations we have discussed so far, but assembler supports these pseudo operations, things we saw with scanf and printf. So if you want to look at more details, you can actually go and look at them. You can search for these things on Google and have a look at them. Was it clear the way you use byte operations, half word operations, and then scanf, printf, all that? Can we go ahead? So the next part we are going to talk about, you'll go ahead. The next part we are going to talk about, it's not something specific to assembly, ARM assembly. This is to give you some general idea about how a program is compiled and loaded and how it is executed. So a brief idea about it. So more details about this loading and stuff, you will talk about them in operating system course as well. But the basic things you need to know how a program is compiled and how it is different from assembly and things like that. So this actually is about compiling and assembling and then linking and loading a program to memory to execute it. So translation and startup. So this is what we are going to talk about, how a program is translated into binary machine code and then how it is going to be executed. So the first thing we actually, here we are talking about from the C level, C program level. In this course, actually, we started from the assembly language level. So if you are starting with C program, a compiler has to be there. So the job of compiler is it converts this high level C program into a assembly language program, which is actually a complex task, because all these things you are doing in assembly manually, the compiler has to do all that. And also it is performing some optimizations. So when you have the program in C, it can do several optimizations to improve the performance and also memory usage and all that it has to consider. So the compilers today are very intelligent, and they can produce optimized assembly code. But there are certain situations you can't do things in C. When you go into fine details or fine areas in operating systems and things like that, you need to use assembly to get things done. So that is also one reason that you learned assembly, and also you need to know how things happen under the hood. So that all that knowledge you gained with assembly. And compiler, it generates assembly language program, and then there comes the assembler. All it does is it takes this assembly language programming and converts it to machine language module, that is ones and zeros. So assembly language is assembly program is in character English. It has these add, sub, or these English words now. So the computer can't understand all that as well. So it has to convert map. It's more like a mapping between this to this. It's not like a complex thing that the compiler does. It's a mapping between these instructions to ones and zeros. So assembler does that job, and many compilers produce object modules directly. So you don't need to first compile and then do the assembling using two commands. When you just compile using GCC command, if you can remember, it actually compiles and assembles. All these things are done by the compiler. And now we have the object code, that is a machine language module corresponding to our program, the program that we wrote, right? And then it's not enough sometimes, because if you are using library routines or library functions, things like printf and scanf, now you are not the one who wrote all these things, so you need to get the implementation of those library functions as well. So actually the compiled library functions you can have in the operating system, so you don't need to compile them again and again, because the same implementation every other program is going to use now. So you have the object code generated for library routines, and then you need to link these two together. because in your program you are using printf, and then there has to be a printf implementation. The code for the printf, it has to be there somewhere in the full program. So that linking is done by this linker, and this linking that we are talking here is actually static linking, where we plug that object code of the library routines into the machine language module of our program. That is like you are appending that to our machine language module, that is linking those two things together in a static manner, and you produce this executable machine language program, the full machine language program that is ready to be executed by the processor. So now you have that is also again stored in a medium like hard drive or something else, flash drive or anything like that. And when you want to execute it, you want to first load it into the memory. These instructions, you need to load them into the memory. So that is the next step you need to do. Using that, the special program that we have for that loading is called loader. So loader does that job of getting the executable code and loading it into the memory, instruction memory. And then from the instruction memory, we'll be fetching instructions one after the other and execute them. And also if you have branch instructions, you will be going here and there in the instruction memory and execute them. So that is the translation and start. So the basic steps of static linking and loading the program to memory. Hope it was clear. So that basic idea, actually, if you have it, that's good. Right. And then producing an object module. Regarding that object module, producing an object module, we talk about that here. So these things actually I talked about earlier as well. So assembler or compiler translates program into machine instructions and provides information for building a complete program from the pieces. So this producing of an object module contains these steps. So it actually builds a complete program from the pieces in the assembly program. Or if it is C, then you have to convert it into assembly first and then do this. Right. So a header described contents of object module. So in the object module, you can see these parts. Header, it contains the contents of the described contents of object module, what it is going to have and things like that. So the size of the program and things like that it could contain. So more details about them, if you want to look at them, you can use Google and look into them. And the text segment, this is translated instructions. So that is text segment of the object module is going to contain your translated instructions. That is the machine code for the instructions that you have in your program. And then static data segment. This one we talked about earlier as well. Data allocated for the life of the program. So this is where actually we were storing these formatting strings used in printf, scanf, and things like that. So static data segment also you have, and that is used to store the data allocated for the life of the program. They are going to be throughout the life of the program. And relocation info for contents that depend on the absolute location of loaded program. So if there are contents that depends on absolute location, that is when you load the program to the memory, if it depends on the absolute location, things like labels and addresses corresponding to labels, things like that could be examples to this. And there could be many, like more situations where it needs to know the absolute location of the locations of the loaded program. So for that, we have this relocation info, and then symbol table, global definitions and external references, debug info, this one for associating with source code. If you are going to use a debugger to debug your code, then you have to associate with the source code as well. this line. So this line in source code maps to this one in the instructions converted into assembly. So that information is going to be stored in the debug info section of your object module. So these are like general stuff you need to know. And then linking object modules, then the linkers job, what it does. So it has to the object producing object module is the first step, and then linking different object modules together to produce a single executable file image. So it merges segments. So that also we talked about. So printf, scanf, all that are going to be, those segments are going to be merged with your code, and segments are merged, and then resolve labels. So if you are using labels, determining the addresses, actually labels you have. So BL, printf, things like that you are doing with labels. Now when you are linking this one, you have to look at the correct address corresponding to that label and resolve it, actually, so that the processor can execute it properly. So it can only identify addresses, numbers, and things like that. No, it cannot identify these printf labels. So these labels have to be converted into actual addresses. So patch location dependent and external references, this is also done. And could leave location dependencies for fixing via relocating loader. So these things also are fine details. So when you talk about virtual memory and how you load a program in using by the operating system, so you will learn about these things. Hopefully you will learn about these things later. Program can be loaded into absolute location in virtual memory space. Virtual memory, I think you are going to discuss them in this course as well. Have you discussed them yet? No, haven't. I think you will discuss them. When you discuss about them in the lectures, it will be more clear. And these are general stuff. And then loading a program. Now we are done with we are done with object module, producing the object module, and then linking. And now we come to the part where we load the program into the memory. So load from image file on disk into memory. So now the compiled full and linked full program is there with us. That is the machine code of the full program. Now we need to load this program into the memory from disk. For that, first thing is to read the header to determine segment sizes. That is, the header is going to contain the size of each segment you have in the object, the final machine code. What is the size of the text segment, what is the size of the data segment, and things like that are going to be contained in the header. And it is read by the loader, and it then creates the virtual address space required for your program, and then copy text and initialize data into memory. So text segment, you need to copy it into memory because that is the part that contains the instructions. And also these initialized data, those things also you need to load into the memory. So these printf, scanf, strings we looked at earlier, those things also, they have to be loaded first into the memory. Or set page tables entries, so they can be folded in. So page tables and all that also you will discuss later. And set up arguments on stack. Now another thing is, when you load the program, this fourth step also is important. Set up arguments on stack. So when you are calling a program, you have seen, I think, command line arguments. Have you seen? I think you have seen command line arguments. You can give them when you are calling, like executing a program, a compiled program. When you execute that program in Linux, you can see you have used these commands like / your program name, and then after a space you specify some arguments. These are specific, like special arguments that we call command line arguments. So they are going to be actually those are command line arguments that are going to be passed to this main function that you call. The first thing, like when you execute the program, what it executes is this main function, right? So for the main function, you are passing these arguments. So when you want to use these arguments inside the program, you have used this int main, then inside brackets, within brackets, you have this char star arg, that thing you have, no? So that is to get the arguments from the command line. Now these arguments are going to be set up on the stack. So these arguments, we set up them in the stack when the program is loaded onto the memory. That is when somebody is going to execute the program is going to get loaded into the memory, and the arguments are going to they have to be set up in the stack. And then initialize registers. This register file, the register file, you have to initialize it to zeros maybe, that you have to do. And then jump to startup routine, copies arguments to R node and calls main. Now jump to startup routine contains 2 steps, copies arguments to R node. So now arguments are there in the stack, on the stack, and the main functions, the arguments to it are the command line arguments. Now loader first loads them or set up them in the stack, and then when it needs to, when it tries to call the main function, just like you pass an argument to another function in C, like in assembly, you need to copy these arguments to R0, R1, R2, R3, these registers, so that main function can read them as arguments. So R0, R1, R2, R3 registers are loaded with values that were set up in the stack, and then main call, the main function is called. And when main returns, startup terminates with exit system call. So when the main function returns, the startup process terminates with exit system call. So that is how you return from the main function and exit your program. So that is it. And then there's again a brief idea about what this dynamic linking is. So all this, like so far we have been talking about actually this loading. Yeah, so far we have been talking about static linking and loading it. Now here comes another concept called dynamic linking. So this one, now in static linking, if you can remember, in the linker stage here, we first got our machine language module that is corresponding to our program, and then the library routines compiled into machine code, and then we link them statically. That is, you combine these two programs together and produce a single executable that contains all these things, all these implementations. In dynamic linking, we don't produce such a executable. We link or load the library procedures when it is called only. That is, at the compilation time, we don't link them statically into the program. That is, we don't combine them together statically, but we load them when it is called. We link them when it is called at the execution time. So requires procedure code to be relocatable. And this procedure meaning the library procedures or the library functions, they have to be relocatable, and avoids image bloat caused by static linking of all transitively referenced libraries. Now, for example, if you have a program that uses these printf, scanf functions and also some other functions that are common to a lot of programs, if you do it with static linking, there are going to be redundant code. That is, printf implementation is going to be stored in your program 1, 2, 3, 4. In all these programs, you have the implementation of these library functions. link to it by the static link. But this we can get rid of this thing, the duplicates, by using dynamic linking, where we have a single code loaded, and when you want to call that function, we use that common function loaded into the memory in one place. So automatically picks up new library versions, and with this, actually, since we are not statically linking it, it can pick up the new library versions automatically, because the implementations, the implementation of the library function, we are not going to have it in a hard code, like a we are not going to have it linked statically in the program. So when we want to call it only, we use it, which is loaded separately to the program. So the library version, the library function, we can upgrade it. The library function can separately be upgraded, and we don't need to compile our code again, compile and link our code again, because it links to the this library function at the execution time. So it can automatically pick up new library versions. So if you have seen these DLLs in Windows, these things actually are these dynamically linked libraries. DLL stands for that. So DLLs are usually loaded onto the, so you have to, so when you, if you have experienced this, when you try to run a certain program, you get this error, this DLL is not found. That is because that library function or a dynamically linked function has to be there in your computer. So if it, so the program does not contain that implementation in it, so it expects it to be there separately. So operating system handles all this linking stuff. So that is why you are getting this error, DLL not found and all that. So you need to separately install that DLL, and then your application can run properly. So that is it. So this is about dynamic linking, and then this lazy linkage, this again fine details. This also you don't need to really focus about this at this stage. Maybe when you come to the virtual memory and then loading a program to loading and linking program on memory, and when you come to find details about that in the lectures, you will understand this as well. If I go ahead and explain this now, it will be a mess. So I'll leave that for you, and that's all we wanted to cover today. So any questions so far? So this linking, this translation and startup thing, actually you need to get a general idea about how things happen, and fine details you can actually look into them when you come to courses like operating systems as well. These linking, so these static link and all that, actually you need to have a idea about all that. So that's it, and I'll actually, yeah, lab 4, is it already uploaded to Fields? Doctor, so maybe any questions so far? If you have any questions related to the stuff we covered today, you can ask. And for the lab, actually, you need to have the knowledge that we covered earlier regarding character data, and then byte half word loading, and then printf scanf. Mostly it's printf scanf. Yeah. Right, now you can see the lab 4 sheet and also there's a x86 executable binary which you can use to test your program actually. So you can run that. That is a executable. That is a program that is ready to get executed. It does not contain the source code, of course, and it is not ARM. That is x86. So this is, you can easily just execute it by using the syntax, using the command that you use to execute a program, / that thing, you know, if you are executing it on Linux. So that is given to test your program. And the first one is actually about reversing a string. Reversing a string. So for that you need to handle the stack and also printf, like scanf and then printf, all that you need to use. And you need to handle these invalid inputs as well. When the user gives invalid inputs, you need to tell that as well, give a warning or an error. Test cases actually are given in the lab sheet as well. An example run is given there as well. And you are free to use library functions, that is printf, scanf, all that you can use. Look at it, have a look at it, and let us know if you come into any issues, get into any issues. Since you have been given the template as well, make sure you follow that as well, the way you need to take inputs and the lines that you need to print to the standard output. All that are given in the example run with an example run. So make sure you follow that. Okay, so if you don't have any more questions, I think we can wrap up the session. And if you get into any issues, you can use the chat or the forum and reach us. Thank you for joining. So I'll end the session now. Thank you. Bye.